For the last 50 years, whenever we've wanted to make a database faster, the answer has always been pretty simple. Just add more. More memory, more CPUs, more servers. We just kept throwing more and more classical hardware at the problem. But we've kind of hit a wall, a fundamental wall.
Okay, so let's get right into it. The reason we've hit that wall really boils down to this one core difference. A classical computer, I don't care how powerful it is, it still has to check data sequentially. It looks at one thing, then the next, then the next. A quantum search, though, it works on a totally different principle: superposition. It can basically exist in multiple states at once, which lets it check a whole lot of possibilities at the same time.
I love this analogy. Think of your database as a gigantic library, and your query is you looking for one specific book. A classical computer is that librarian, right? Methodically walking down every single aisle, checking every single book, one by one, until it finds what you're looking for. It works, but man, is it slow. But what if that librarian could stand in every single aisle, looking at every single book, all at the exact same moment? What would that even make possible? Well, to find the answer, our story doesn't start in some Silicon Valley data center. Nope, we have to go back to 1981, with a physicist who wasn't trying to build a better database at all. He was just trying to understand reality itself. So in 1981, the brilliant physicist Richard Feynman had this profound realization. Nature isn't classical, it's quantum. And he figured if you want to properly simulate the quantum mechanics of nature, you can't use a classical computer. You need a computer that actually behaves like an atom does. And get this, while he's working on this theory, the rest of the tech world is busy building the relational databases like Oracle and SQL Server that still pretty much run our world today. You can just see these two completely separate paths unfolding at the same time. And that's the crucial point here. While the commercial world was all about scaling up, just making bigger and faster versions of what they already had, physicists were off in a corner, quietly working on a completely different paradigm. I mean, they were trapping ions, cooling circuits to near absolute zero, basically bending the rules of logic. They weren't just building a faster computer. They were building an entirely different kind of universe for computation to live in. For years, this was all just theoretical physics, stuff for chalkboards and academic papers. But then came the moment when this new universe found its killer app, an application so powerful it promised to completely change the world of data forever. And that killer app was Grover's algorithm, which showed up in 1996. Its purpose was simple, but absolutely revolutionary: search a huge, completely unsorted database. And it proved that a quantum computer could do this dramatically. I mean, almost unbelievably faster than any classical computer ever could.
And this chart just illustrates the difference perfectly. So let's take a table with a million rows. A classical machine, in the worst-case scenario, might have to check every single one of those million rows. That's a million steps. A quantum machine using Grover's algorithm, it needs about 1,000 steps. That's not just a little faster, that's a whole different ballgame. It's a fundamental leap.
This quote just nails it. Imagine trying to find one page in a giant book that has no index. Classically, you have to flip through page by page. Quantumly, it's like you have this weird intuition that just lets you open the book to the exact right page on the first try. You don't need any of those complex indexing structures like B-trees to organize the data beforehand. It's just bam, instant access. Okay, so this all sounds incredible, right? It sounds like the future we were promised in movies. Which of course leads to the obvious question. If this tech is so powerful, where is it? Why aren't we all using it? Well, there's a catch. A very, very big one. It's a totally fair question. Why isn't this technology in your pocket right now, or on your laptop, or running the servers you're connecting to? The answer lies in just how impossibly delicate the quantum world really is. The problem has a name: decoherence. You see, quantum states are unbelievably fragile. A tiny vibration in the floor, a slight change in temperature, even a single stray photon of light bouncing into it can be enough to make the entire computation collapse and lose all its quantum magic. It's really like trying to build a sandcastle during a hurricane. And that brings us to where we are today. We're in what people call the NISQ era, which stands for Noisy Intermediate Scale Quantum. Basically, we can build quantum computers, but they're noisy. They're incredibly prone to all those errors from decoherence. Honestly, you can think of them as the ENIACs of our time. These massive, room-sized, super delicate machines that are really just the very first step into a whole new age of computing. So here's the bottom line. We are absolutely at the very, very beginning.
We are in the ENIAC era of quantum. The machines are noisy, they're imperfect. But if the history of technology has taught us anything, it's that we go from ENIAC to the iPhone. So the real question isn't if this is going to change our world of data. The question is, who's going to be ready when it does?